Hello everyone, and welcome back to the channel. Today, we are diving into one of the most fundamental concepts in organic chemistry, resonance, also known as the Mesomeric Effect. If you've ever wondered why some molecules are more stable than they look on paper, or why certain reactions happen at specific positions on a benzene ring, the answer lies in the movement of electrons. By the end of this video, you'll be able to identify, draw, and predict the effects of resonance with ease. Let's get started. Let's see what is resonance. See the structure of benzene or ozone. In many cases, a single Lewis structure cannot accurately represent a molecule. Resonance occurs when the polarity of a molecule is produced by the interaction between a lone pair of electrons in a pi bond, or between two pi bonds in adjacent atoms. Key rules for resonance: only electrons, pi electrons and lone pairs, move, atoms never move. The total number of electrons and the overall charge must remain the same. Resonance structures are not real. The real molecule is a resonance hybrid, a weighted average of all structures. Now we will see how the plus M effect works. Electron donating groups. The plus M effect occurs when a group donates electrons to the conjugated system through delocalization. These groups usually have a lone pair of electrons. In this mechanism and resonance we can see step-by-step visual delocalization of the nitrogen lone pair into the aromatic ring, showing how specific resonance structures create high electron density at the ortho and para positions. So guys, this visualization's showing the resulting partial negative charges in an electron density map, heat map, of phenol, alongside a comparison chart illustrating increased reactivity toward electrophiles compared to unsubstituted benzene. In this common groups are O, OR, NH_2, NHR, Cl, bridge. Let's check how it works when attached to a benzene ring. These groups increase the electron density on the ring, particularly at the ortho and para positions. This makes the ring more reactive toward electrophiles. After M+ effect, now we will try to understand the M effect, electron withdrawing groups. On the other hand, the M effect occurs when a group withdraws electrons from the conjugated system toward itself. The electron withdrawing groups like number 2, Cn, CHO, COOH, and SO3H. Mechanism and resonance. A step-by-step breakdown using nitrobenzene, showing how the NO2 group pulls pi electrons out of the ring, creating positive charges at the ortho and para positions, while the meta position remains unaffected. A comparison using heat maps of electron density, contrasting unsubstituted benzene, electron-rich, warm colors, with nitrobenzene, electron-poor, cool colors. This visual confirms that the meta position is relatively more electron-rich, explaining why negative M groups are meta-directors for incoming electrophiles, E+. The final bar chart illustrates the deactivating nature of these groups, making the ring less reactive. Number 2, Cn, CHO, COOH, SO3H. Let's see how it works. So these groups pull electron density away from the ring. This decreases the electron density, especially at the ortho and para positions, leaving the meta position relatively more electron-rich. Let's understand the conditions for resonance, conjugation. Resonance doesn't just happen anywhere. It requires a conjugated system. Look for these patterns in your molecules. 1. Pi, sigma, pi, alternating double bonds. 2. Pi, sigma, lone pair. 3. Pi, sigma, positive charge. 4. Pi, sigma, free radical. Now we will try to learn application and stability. Why does this matter? Because resonance increases stability. The more resonance structures you can draw for a molecule, the more stable it usually is. This explains why the phenoxide ion is more stable than ethanol, or why carboxylic acids are acidic. Understanding resonance enhances stability. The fundamental idea is that electrons are more stable when they are not confined to a small region or a single atom, localized. Resonance delocalization allows excess electronic charge to be spread over multiple atoms or bonds. Think of it like distributing a weight over a larger area. The same burden feels lighter for each individual supporting it. For a molecule or ion, this spreading out of charge density reduces high concentrations of electrical potential, lowering the overall potential energy and making the species significantly more stable and less reactive. More structures equals generally more stability. While not always a simple case of counting structures as equivalents and electronegativity matter too, having more valid resonance contributors generally increases the overall resonance stabilization. The actual structure is a hybrid, and the existence of multiple possible forms indicates greater possibilities for delocalization. After all the explanations, we will take one examples and acidity one. Phenoxide ion versus alcohol base, e.g., ethoxide ion, O and alcohol deprotonates to form an alkoxide ion, like ethoxide. This ion has its negative charge localized entirely on a single oxygen atom. OA phenol deprotonates to form the phenoxide ion. For this ion, you can draw multiple main resonance structures where the negative charge is distributed not only on the oxygen but also across 3 carbon atoms in the benzene ring, the ortho and para positions. This significant delocalization makes the phenoxide ion much more stable than an alkoxide ion. This stability explains why phenols are thousands of times more acidic than simple alcohols. 2. Carboxylic acids. O. When a carboxylic acid deprotonates, it forms a carboxylate ion. While you only draw 2 main resonance structures for this ion, they are unique in that the negative charge is delocalized perfectly equally over 2 highly electronegative oxygen atoms. The equivalence and high electronegativity make this stabilization extremely effective, explaining why carboxylic acids are much stronger acids than either alcohols or phenols. Blank. Blank. Let's conclude the call to action. To wrap up, resonance is the delocalization of pi electrons, and the Mesomeric effect describes how specific groups push or pull that electron density. Mastering these patterns is your cheat code for organic reaction mechanisms. If you found this breakdown helpful, please hit the like button and subscribe to Chemistry with Harshada for more masterclasses. If you have questions about specific groups or mechanisms, leave a comment below. I'd love to help. See you in the next lecture. Thank you for watching this video. Please like, share and subscribe Chemistry with Harshada if you like this video.